got a couple of things to finish up in this packet that we were working on. Measurements and ratios packet. Does anybody have any questions off of the problems we've done in it so far? Mechanical advantage or the aspect ratios, anything like that? So, two things I want to finish up. One is electricity. Actually, there's three. Electricity is all about ratios, but it depends on what type of circuit we have. This is a simple circuit. One voltage source, one load or one resistance, and then there's current. I don't know why we use I for current. C is there for charge, so I guess that's why we use I for current. It would make sense to use A for amperage, but anyway, I is what we use for current. There's a relationship there. Voltage is equal to current times resistance. This is voltage consumed, or dissipated is the word they use. So whatever current, let's say this has 2 amps of current, and our resistance here is 60. Now this upside down horseshoe type thing is the symbol for ohms. 60 ohms of resistance. The voltage is 2 times 60, or 120 volts. Makes sense if you're producing 120 volts, that's what's. So that means here the voltage source, and of course, it's your typical conservation law. Whatever voltage is produced has to be consumed. Zero total voltage. So you produce 120 volts here, there has to be 120 volts consumed or dissipated across that load. We have more than one load. I'm going to label these R with a little 1 and R with a little 2. Resistor 1, resistor 2. I'm marking it with a simple symbol for resistance right now because basically that's what a load amounts to in a circuit, is a source of resistance or impedance. That could be an electric motor, could be a light bulb, could be whatever. Could actually be a resistor if we want to regulate the voltage. Now let's just say that we have 120 volts here again. Up here, we could have found the current if we wanted to by doing the voltage divided by the resistance, working this formula backwards, solving the equation. Down here, however, we have 2 resistances. We have to have some way to combine them. Let's say that this resistance here is 10 ohms. This resistance here is 20 ohms. When we look at a circuit with multiple loads, multiple resistances, we have to look for what remains constant. In this case, current. Whatever current flows through this resistor has to also flow through that resistor, right? Current has to remain constant. Second question to that then is, what is divided? Well, only thing left, the resistances are set. Those don't change. These are not variable resistors. If the current has to remain constant, the only thing left is the voltage that's going to get divided. Now here I will tell you that the current is 4 amps, which means the voltage across this resistor, 4 times 10, which is 40. So there's 40 volts there that makes a difference, dissipated across that resistor. For this resistor, the voltage is still 4 amps times 20 ohms now, which is how many volts? Now that adds up to 120, so we're good. Notice that the ratio of voltage, 40 volts to 80 volts, is equal to the ratio of resistances, 10 ohms to 20 ohms. This is what is referred to as a series circuit. The loads or the resistances are in series, one after another. And the characteristic is the current has to flow through both of them. So the current stays constant. So it is constant current is referred to as a voltage divider. Probably heard the other term that comes up, parallel circuit. Now the terms series and parallel. Series means one after another. So this one is series because the current flows through one resistor after the other. Parallel means at the same time. So in a parallel circuit, people think that it's called that because the two resistors or two loads are parallel to each other. Not necessarily true. It's called a parallel circuit because current flows through both loads at the same time, parallel. I have a current here. I'm going to call this total current here, IT. Resistor 1, resistor 2. This is current 1 and current 2, my personal voltage. I'm going to stick with 120 volts. Now, if I have 30 ohms and 60 ohms by resistors. Remember, we said the first question is what remains constant? Second question is what is divided? The answer to that second question seems pretty obvious here. It's the current that's divided. We have our total current here, and at this point, half of it goes, or part of it goes this way, part of it goes that way. I can't say half because it won't be half. So the current is divided. Voltage that must stay constant. Both loads here, assuming we have enough power in our power source, will experience the same voltage. This voltage across here, 120 volts. Across here will be also 120 volts. Which means this current, 120 volts equals I1 times 30. How do we solve for I? By 30. 4 equals I, or I1. So this is 4 amps of current here. This current, 120, I2 times 60 is the ohms. How do we find I? I60. 2 equals I2. 2 amps. Which means that I total has to be, those two just add up. 4 plus 2 is 6 amps. What you see is the voltage stayed constant. The voltage stayed the same, 120 volts across each, 120 volts produced and 120 volts across each piece. Current was divided. And you notice it's inverse here. Smaller resistor got larger current. Bigger resistor got smaller current. Think of it as like water flowing down a hill. It's going to take the easiest path. So the path with least resistance is going to get more water flowing down it than a harder path. But notice the total resistance for this whole circuit. 120 volts equals 6 amps times the total resistance. What's that total resistance going to have to be? Or how do we find the total resistance? By 6, 20 ohms. Total resistance is smaller than either of the given resistance. We had 30 and 60. We have a total resistance smaller than either one of them. Because we're allowed to have current flowing through each of them separately. In parallel or at the same time. You guys actually used to have a science course when it was a 2-year machine tool program. Used to have a science course where we did quite a bit of the electricity stuff. I miss teaching that course. That was a fun one. We not only did the basic circuits and stuff like that, but we also did the power consumption, cost it to the home and stuff like that, how to figure out how much an appliance, what it's actually costing you to run an appliance, stuff like that. We won't get into that here, though. That's not our purpose. So anyway, one of the other things we want to talk about is temperature. We talked a little bit last semester about temperature conversions and how it is different from any other measurement conversion. All of our measurement conversions are basically a ratio. The way we did them was we used conversion factor called dimensional analysis. If we had 4 feet, made that a fraction, if we're converting to inches, we use a conversion factor where we put feet on bottom so they cancel out, inches on top. 1 foot is 12 inches. Feet cancel out. 4 times 12 inches is 48 inches. 1 times 1 is 1. So that's 48 inches. Again, that process is called dimensional analysis. It's called dimensional analysis is because it's the dimension that determines your conversion factor. You've got feet, you're getting rid of feet, so you have to put feet on bottom of your conversion factor so it cancels out. Going to inches, so you put them on top, so that's what you end up with. In the medical fields, dimensional analysis is huge. That's how they do all their dosage calculations and stuff like that, is they use those types of conversion factors. For our purposes, there's actually another way we could have done those conversions. 12 inches equals 1 foot. On the other side over here, so this is our equivalency, the 12 inches equals. That's our first rate. Not a ratio because it's different units, but it's our first rate. On the other side, we're starting off with 4 feet. That has to go with the feet, so it's going to go on bottom. Find how many inches that converts to. We cross, multiply, and divide. 4 inches, or 12 inches times 4 feet is 48 inch feet. That's an actual unit. Divided by 1 foot, divides out the feet, that's 48 inches. So we can do measurement conversions that way as well. Well, this all breaks down when we get to temperature. Our benchmarks when we look at temperature are water boils and water freezes. I heard you say it over there. What temperature does water boil at? 212 degrees Fahrenheit. Freezes? 32. This time of year, it's pretty hard to forget that one, isn't it? You'd be amazed at how many classes don't know the temperature water boils. When we were in 5th or 6th grade, we had to memorize all that stuff. You know, when does water, what temperature water boil, freeze, mile, yards in a mile, all that stuff. In the Celsius scale, what temperature does water freeze at? 0 degrees Celsius. And boils? 100 degrees Celsius. For that reason, it's sometimes called the centigrade scale. Centi means 100, grade means division. So it's a scale of 100 divisions between freezing and thawing for water. That name has kind of fallen. We look at each of those. Difference for Fahrenheit, from freezing till thaw to boiling, 180 degrees Fahrenheit. Celsius is only 100 degrees, like we said. So that gives us a conversion, that a difference of, a change of, this little symbol, the triangle, called delta, means change of. A change of 180 degrees Fahrenheit is equivalent to a change of 100 degrees Celsius. If I turn that into a ratio, 100 over 180 would be 5 to 9. Or 180 over 100, 5. 5 by 20 would be 5 and 9. Problem is, as we mentioned last semester, no common 0 point. For all these conversions we've done before, inches and feet, 0 inches equals 0 feet. They have a common 0 point. 0 gallons equals 0 fluid ounces. There's a common 0 point there. 0 pounds equals 0 ounces. 0 grams, or whatever we're going to measure it. 0 grains. Temperature, there's no common 0 point. 0 degrees Celsius does not equal 0 degrees Fahrenheit. So because of that, we can't just use a simple conversion factor. We can't use a simple proportion or a dimensional analysis conversion factor. We have to use those formulas. Convert from Fahrenheit to Celsius. Start out with our Fahrenheit temperature. And the first thing we have to do, bring it down, find that common 0 point. The difference between the 0 points is 32 degrees. So we would subtract 32 degrees. And then we would multiply by that ratio of 5 ninths. The temperature in degrees Celsius is 5 ninths times the Fahrenheit temperature minus 32. So what was it today, like 14 degrees out there or something like that? Like I said, it wasn't that cold, it just felt really cold for some reason. I've always figured down to 10 degrees I'm pretty good as far as being outside and doing stuff. It was over 10 degrees and I was not good out there this morning. So we put that in here for F. -14 - 32 is going to give us a -18. Now I'm going to keep the parentheses in there, not because I need them as an enclosing symbol, but because that's a negative number. I need to that negative number isolated so I know it's multiplied here. And then 5 ninths times -18 is -10. So that 14 degrees Fahrenheit today would be -10 degrees Celsius. Sounds even colder.
Yeah.
Converting from Celsius to Fahrenheit, we reverse the process. If I were solving this, if I had a number in here for Celsius, now let's just throw in 20 degrees. If I wanted to solve this for Fahrenheit, what I could do, now, the way we normally do is we distribute the 5/9 and then solve it. But we could, in this case, we could actually divide by the 5/9 or multiply by 9/5. 9/5 times 20 degrees. F minus 32. And then add the 32, right? What we just did there is the formula you get from Celsius to Fahrenheit. Fahrenheit temperature, if we know the Celsius temperature, it's 9/5, sorry, times the Celsius temperature. And then add 32 to it. It's just in the backwards order. Here, we subtracted 32 first and then multiplied by 5/9. Down here, we divide by 5/9 or multiply by 9/5 and then add the 32. So the reverse order. So we put the 20 degrees in there for Celsius. Nine fifths times 20 is 36 degrees. Plus 32 is, sounds incredible right now. Actually, I prefer about 60 to 70 degrees all year round. I don't care if I get above 80. I might be built for the cold a little better than the heat. I won't make you do it. I won't be that cruel. But the one example I like to use, several years ago, a friend of mine asked me, he was an administrator at a high school, asked me to come in and do a demonstration because based on the metric system. And one of the topics was degrees Celsius. And it was just a quick, 20-minute demonstration, little mini lecture for parent-teachers conferences. Because this was 15 years ago, he thought there was going to be a huge push to get converted over to the metric system. Now, yeah, 30 some years ago, 34, 35 years ago, sitting in my middle school science class, my middle school teacher was saying, within 10 years, the U.S. is going to be on the metric system. It hasn't happened. But anyway, one of the comments that was made, and I had to chuckle, nobody else in the room understood why it was funny, was, looking at how it contracts the temperatures and it's all closer because the degrees are larger. Made the comment, well, I guess there won't be any more of those minus 40 degree days. Well, you get why it's funny?
Yeah.
Yeah, negative 40 is the one temperature that's the same in both scales. Inverted is the same. Nobody else in the room had any clue why I was chuckling when he said that. So, actually, let's do this. Let's say that we have a mixture, a solution we need to create. We need 5 pounds of this chemical mixed into 4 gallons of water. We want to mix it on a smaller scale. And let's say we want to know how much should be mixed into 3 quarts. How many ounces is it going to take to go into 3 quarts? Well, when we are dealing with a proportion, we need one of 2 things. Either the labels on these 2 items have to be the same, which means then the labels here would have to be the same. But this could be both pounds and this would be both ounces or both gallons or whatever, but it'd have to be the same. Or the label on these 2 items has to be the same, and then these 2 would have to be. Here we don't have that common label in either direction, which means we got to change something. This is not a valid proportion right now. Generally, it is easier to go to the smaller unit. So we're going to convert 5 pounds, ounces. 5 pounds over 1. Pounds are on bottom, so they cancel out. 1 pound is how many ounces? Pounds cancel out. 5 times 16 is 80 ounces. To redo this, I'm going to put 80 ounces on top. For the bottom unit, which is the smaller unit, gallons or quarts? Quarts. So I'm going to convert my gallons into quarts. For gallons, put it over 1. Gallons on bottom going into quarts. 1 gallon is the bigger unit. How many quarts are in a gallon? 4. 4. Gallons cancel out. 4 times 4 quarts is 16. This becomes 16 quarts here. First, this stays. Now we can cross multiply and divide. 80 times 3 divided by 16. So when we're dealing with these proportions, this is not a valid proportion because we don't have the same units in either direction. This one's a valid proportion because we got ounces and ounces on top, quarts and quarts on bottom. That should be all the information you need to finish this packet. I realize we've been working on it for like 2 weeks now, so probably be a relief to get it over with. Thursday, February 4th, that's tomorrow, is test 1, unit 1 test. I will give you that today here before you leave the room so you have it with you. You don't have to print it off. We're missing just Des and Chase, right? I will leave 2 copies out on the table. I'll put them on the front table up here so if they do come in tomorrow morning, they can grab them, not have to print them. How many of you plan on coming in anyway tomorrow? Well, some people would just, use it to sleep in and come in. It doesn't matter. I will be logged onto the network anyway, but there won't be any lecture, no new homework or anything. I'll be on the network just to answer questions. You might see me doing stuff in the background. I'm in the process of packing up my house right now. So you might have to yell at me if you have a question to get my attention. I will be there. The other thing is I'm going to also give you guys that are here, I'll give you the packet for next week. Okay, so we're going to end the recording here and I'll start passing stuff out for you if you guys want to